Let us today discuss about the DFS algorithm. Depth first search DFS is an algorithm for traversing or searching tree or graph data structures. The algorithm starts at the root node, selecting some arbitrary node as a root node in the case of a graph, and explores as far as possible along each branch before backtracking. It traverses a graph in a depthward motion and uses a stack to remember to get the next vertex to start a search when a dead end occurs in any iteration. DFS follows a working flow which is mentioned with an example on the slide. Here, each of the vertices is visited in a downward location in a successive fashion. DFS uses a stack for its operation and implementations. DFS follows a three-step working procedure and includes the following three steps as mentioned in the slide. Rule 1. Visit the adjacent unvisited vertex, mark it as visited, display it, insert it in a queue. Rule 2. If no adjacent vertex is found, remove the first vertex from the queue. Rule 3. Repeat Rule 1 and Rule 2 until the queue is empty. The following pseudo code explains the algorithm very well. We first begin the code and initially mark all the nodes as unvisited, then push the start element into the stack. We then perform an iterative while loop which continues working until the stack is not empty. Here we first pop the element from the stack and set it as U, and then we display the node U. We then use a conditional statement and check if U is not visited. Then we mark U as visited. For all the nodes I connected to U, we check if the ith vertex is unvisited. Then we push the ith vertex into the stack and mark it as visited. Then we display that we are done with all the operations and then enter procedure. Here is the typical example of a DFS wherein we followed the three-step procedure for each iteration. In the first iteration, we get the value 10, followed by 20, 40, followed by 50, and finally 30 and 60. There are various applications of DFS, some of which include finding connected components, topological sorting, finding bridges in graphs, finding biconnectivity in graphs, and cycle detecting.